Okay, so let's get started with the second part of chapter 31. We're going to begin with damped oscillations in an RLC circuit. So that's going to have a resistor, an inductor, and a capacitor. Before we do that, let's just briefly discuss damped oscillations in a block spring system. That's the worst G I've ever drawn. And so let's get a good picture of what's going on here. Let's say we have a block and a spring, M, K. And there's two different ways you could think about it. Right, you can either say we have some mu sub K on the floor all throughout this oscillation. Or another way people kind of will think about it is they'll say, we're going to take this whole thing and submerge it in some viscous media, right? And so maybe this is full of like honey that's going to slow it down. Right, either way, it's going to have some kind of resistance on it. So I think what we're going to do is we'll just pretend it's submerged in something viscous, right? And we're not going to get into like linear quadratic drag. Like, we're just going to have something that slows it down. So if we take our spring and we extend it really far out, so maybe this was X naught. We still have K. And we have it, right, I guess the light pink will be submerged, and we'll keep the white writing for non-submerged. Right, and so if we had it with no damped oscillation, we would expect this block to move faster than this one, right, initially. And what we expect this block to do is it's going to whatever, right, the maximum amplitude is here. We expect it to reach some negative of that amplitude over here, versus the damped oscillation. If we start off at some maximum amplitude, capital X, we would expect it to maybe not go as far. And so maybe we would get to negative, well, X minus X, right? Or, you know, we can put something else in there that's not an X, right? We could put a L, whatever. And then, you know, on the way back, it's going to get even shorter and shorter and shorter and shorter, and it's going to be going slower and slower and slower and slower. And so a damped oscillation will continuously lose energy to the environment, decreasing max amplitude and speed. Right, and so as we lose energy, then the maximum energy available is going to be lower, and so whether it's all turned into kinetic or potential or some combination, it's going to be continually decreasing, right? And so if we have an undamped oscillation, and let's say we plot the potential energy of the spring as a function of time, right, we expect to do something like this. Once we do have a damping in there, we expect it to, well, yeah. Well, no, that wasn't good at all. Right, so it's still going to go to 0, but then it comes to a lower peak and 0. So maybe like if we did position, that might be easier to see. So let's do the max amplitude. we go from positive to negative. And so we'll just have this be x in meters, t in seconds. And so we'll do positive amplitude, and then we'll do negative amplitude. And so I'm going to do one trace here in white that would show what's going to happen for the undamped case. Right, and we just go back and forward continuously forever. But in the damped case, what we're going to do is we are just going to slowly decrease to 0. All right, and so that's what we expect to see. Something very similar for the block spring system. Right, and so let's say we have our circuit. Where are we going? So let's say we have some inductor L hooked up to some resistor R, a capacitor C, and back home. And so, you know, just like we did in the last video, we're going to start with all of our charge initially on the capacitor. And it's going to go through those LC oscillations we talked about. But now the entire time we're doing that, our resistor is radiating heat out of the system, right? And so what do we know about resistors? Well, we've talked about the energy stored in an inductor and the energy stored in a capacitor. But resistors store no energy. They only dissipate energy. Right? And they do that by converting it into thermal energy or heat. Right? We've seen in lab a handful of times that if you get a resistor or even a wire which has a resistance, it is a resistor. If you run current through it for a long time, it heats up noticeably. Right? And so oftentimes in circuitry, we pop a resistor in there, so that dissipates off more heat than the wires will, right? So that way the wires don't have to deal with that burden. Okay. And so since the resistors store no energy, we can say that the total energy is still going to be U is equal to, the magnetic and the electrical energy, right? The energy stored in those fields. And we said that was going to be L I squared over 2 plus Q squared over 2C. Right, and what we did before was we said the total energy is a constant, so the derivative has to be 0. But now, total energy won't be constant, right? And so we're going to have du dt is not equal to 0. And so we have to think, what is it going to be equal to? What is the change in energy going to be through this system we have here? And well, we've discussed before that the power, right, the rate at which energy is dissipated through a resistor is equal to negative I squared R, right? And the minus sign there is because it's decreasing. And so we can say du dt is equal to negative I squared R, right? And this is equation 3123, in case anyone's super interested. And then we'll note that the minus sign is there because we're decreasing. in the system. Okay. And so we can go ahead and take the derivative of this equation, which I think is 3122. And if we take the derivative of 3122, we get du dt is equal to, right? I'm not going to bother writing this out. And we'll just go straight to, it's equal to Li times di dt plus q over c times dq dt, and we're going to set this as equal to negative I squared r, right? So we have du dt, we have du dt, and so we should be good to go, right? And the reason the halves go away and we take the derivative of the thing squared and we change it to this, it's the same argument I showed with a u sub in the last video. Chain rule would work as well. I just, you know, it's the same exact math. Okay, and so we have this equation, but, well, first off, let's rewrite it in a slightly more friendly way. So we have Li di dt is equal, oh, nope. So now I'm going to say plus I squared r, right? I'm just moving this over into the middle for reasons we'll see in a second. And so we have 1 over c times q times dq dt is now equal to 0. Right, and so now we have something equal to 0. That's always a good thing. And we can make some substitutions, right? We can say current is equal to the change in charge. And then we can say the derivative of current is equal to the second derivative of charge. Right? Nothing new here. And we're going to go ahead and plug those in. And so we have L times an I, which we said is a dq dt. Then we have di dt, which is the second derivative of charge, plus, well, we have I again, so that'll be dq dt squared, right? I is squared, so we just square that, times r, plus 1 over c times q, and then we don't have to change anything here, right? dq dt is equal to 0. And we can go through and say, we'll cancel out a dq dt, a dq dt, dq dt, get all those out of there. And we have L times d squared q dt squared, the second derivative of charge with respect to time, plus the first derivative of charge with respect to time. Actually, we're going to scooch that over just a bit, and we'll put the r in front, and then plus 1 over c times q is equal to 0. And so we're not going to get too far into the diff-EQ of it all. We'll note that this is equation 3124. But let's just investigate what we have going on. We have a thing, the first derivative of that thing, and the second derivative of that thing, right? All with some constants in front of them, right? Some parameters about the system, and that's equal to 0. And so just like we did in the last video where we had, what did we have? We didn't have this middle term here, but we had charge and its second derivative, and we had, okay, like those are going to be equal to 0 with some constants out front. And so we had to think of a thing that its second derivative is the negative of itself, and for that we picked cosine, right? Sine would have worked as well, right? If you take the second derivative of a sine, you get to a cosine. or you get to a negative sign, right? First derivative gets you cosine, second derivative gets you back to negative sign. And so here, you know, diffie Q is not a prereq or a coreq for this class, so we're not going to get too far into it. But the answer of what satisfies this is going to be an exponential, which exponentials and sinusoids are very intimately related. You can rewrite one in terms of others, but again, we'll save that for another day. And so what we end up getting is, if we wanted to solve this differential equation for Q, we would get it's equal to some max value e to the negative RT over 2L times cosine omega prime t plus phi. And this is equation 3125. And so let's see. We have, right, anytime we've seen something like this, we know, oh, this is going to be an oscillating expression, right? And we have our oscillating term, and then we have the amplitude. And I think, you know, we've seen some interesting amplitudes, right? I think when we dealt with superposition of waves, we actually had a cosine in the amplitude, but it was cosine of phi over 2, right? The phase over 2. And so that ends up being like a constant. And so it's not part of the oscillating term. Here we have an amplitude. The exponentially decays. Right? Which is what we more or less expect, right? We expect that as we run this system up here, we are just going to lose and lose and lose the total available charge, right? As we convert that electrical energy into heat. Okay, and so then let's also go ahead and say what omega prime is going to be omega squared minus r over 2L squared and square rooted. Okay, and so let's see, does this make any sense? And then of course, where omega is just the resonant frequency for a LC circuit. And so a lot of times people see this expression here and go, well, what the hell? Why isn't capacitance involved in this? Well, we would expect, well, one, we expect a decrease to the overall frequency, because if we picture our block being in honey, right, it's going to slow down the oscillations just like a resistor is going to slow down the electrical oscillations. Or, you know, friction, drag, you know, whatever you want to damp this oscillation with. You know, you have something that's taking energy out by slowing things down, right? Things are slowed down, so we decrease the frequency. So that should be somewhat comforting. And so we expect the effect of the resistance to have a minus sign opposed, like when it comes into the angle of oscillations we're going to get. But why is inductance in here? Because inductance is like the inertial term in this system. And I believe we saw in the one question we did in class, if you change the inductance, you change the maximum available current in the system, right? I believe we had I max is equal to Q omega, where omega is square root L over C, right? And so as we increase inductance, we decrease omega. If we decrease omega, we decrease I max. And so the inductor is in there to reflect that, right? The higher the inductance, the lower the overall current, and then the slower we dissipate the energy. Okay? And so what does this frequency physically mean? This is going to be like the resonant frequency of this system here. Right, this is the frequency at which these oscillations are going to occur if there's nothing else going on, right? Just like it would be very similar to the frequency at which this oscillation is going to occur if, I'm not coming along and applying an external force every now and then, besides the damping force, right? If I have a driving force, I'm sitting there and smacking it every time it comes to the maximum amplitude, right, that would be me driving it at its resonant frequency, but we'll get into that later. Right, so this is just going to be the frequency a LRC circuit oscillates at. Okay, and so, we discussed that we have essentially we get a sinusoid with an exponentially decreasing amplitude. Right, and so that amplitude we said was going to be equal to QE to the negative RT over 2L. Right, and we see we have this R over 2L here. We have it in the amplitude as well for the exact same reasoning, right? The higher the resistance, the faster we're going to dissipate all this energy. The higher the inductance, the slower we are because it is going to slow down the current and decrease the maximum current. Okay. So, well, let's look at what the electrical energy as a function of time is. And so at any given point, we can say this charge Q, this is the charge on the plates of the capacitor. We will have this energy, right? Q squared over 2C, nothing new there. And so we can go ahead and plug in equation 3125 for that. And so we get QE to the negative RT over 2L. Let's get you out of here. You're about to be in the way, dude. I'm sorry. Times cosine omega prime t plus phi. I totally could have just done the copy thing, but whatever, we're already here. And then that was Q squared. Actually, I feel like square brackets are justified here. And then over 2C, right? We just brought this 2C over. Okay, and so let's go through and square that. Nothing too tricky. And so we get Q squared over 2C times E to the negative RT over L, right? Right, remembering that E to the X squared is E to the 2X. And so the 1/2 we had right here disappears over here because we squared it. And then we obviously square our cosine, right? Can't forget that. And nope. Omega prime t plus phi, because if you square cosine, you just get cosine squared. Okay, and so that tells us that the electrical energy in the system is going to follow a cosine squared oscillation, which that's neat. And so let's say what this actually means in words. And I think this was all 3127. And so the energy, I guess yeah, the energy of the E field oscillates following a cosine squared term and the amplitude of that oscillation decreases exponentially with time. Neat. That's fun. And so that's what we have for chapter 31, section 5. And we'll mess around with this in class. We'll do some problems. And so let's hop into chapter 31, section 6, which is alternating current. You'll often hear people say AC current, which means alternating current. It's just like when people say ATM machine, right? That's automatic teller machine, if they say it that way. But, sometimes it just makes a sentence sound better to say AC current, right? Or you could always just say an alternating current, right? If we had a circuit and we said we apply an AC, it feels like you didn't finish the sentence. But you say we applied an alternating current or an AC current, it makes the sentence sound a bit more complete. Okay. And so little fun facts about alternating current. In North America, right, you plug something into an outlet, you are getting AC out of that. And so we have a frequency equal to 60 hertz, right, which means if you plot, we'll put voltage in volts, time in seconds, right, it's doing that, where from here to here is 1/60th of a second, right? Full oscillation. Or you could say it flips every 120th of a second, right? Because it has to flip twice to do a full oscillation. And so in North America, you can say current flips 120 times per second, which might be raising some questions, right? We discussed earlier that the drift for an electron in a circuit is, I don't want to put an equal sign, I want to put, kind of roughly 10 to the negative 4 to 10 to the negative 6 meters per second. And so if it's going that slow and it's changing direction that fast, how does current ever get anywhere? Well, the important thing to note is that in a circuit, you don't have one electron traversing the whole circuit, right? They are all just kind of going in one direction. If you want, sometimes that's too long. We picture electrons in a circuit like a bunch of marbles in a tube, and if you take an extra one and push it in, then the one on the end pops out, and so it instantaneously travels through the whole circuit, right? So that's one of the ways we kind of think about it, even though that's not entirely correct. A better way to think about it is if you have your wire, you have a bunch of electrons, right, all kind of bouncing around at their Fermi speeds, going fast. If you take a cross section of that, when you have a potential, overall, more electrons are going to travel across the boundary in one way. You might get 2, 3 going this way for every 1 that goes this way. And so when you look at this cross-section, overall, electrons are traveling through it, but they're not really going anywhere at the end of the day. And so it is just the overall motion of charge that makes all of this happen, right? If you have maybe... What? A light bulb, right, hooked up to, I don't know, positive, negative. The electrons that start down here aren't going all the way up through the filament, coming back down, and doing all that. It's just the electrons in the filament are now just kind of moving back and forward with the AC current. See, I said it, AC current, haha. But if I said with the AC, it doesn't sound good. Okay. So that's just kind of a brief intro to what in the world is happening in North America. Well, all right, we're not going to get all the way into that. As far as our currents are concerned. And so let's go ahead and take... I've been using this color a whole bunch. We'll go green for the magnetic field here. And so let's say we have some external magnetic field. We have some wire that is going to rotate about a central axis. Right, so it's going to be constantly going in and out of the plane. Right, we're going to have a changing flux. We expect an EMF. Okay, and so the way these devices typically work is you will have some kind of metallic ring known as a slip ring that is only in contact with one of these wires. So this top one will brush it there, which is then going to be hooked up to another wire going out. And then we also have a slip ring that's in contact with the lower wire here. And you know what? Actually, we can just go, you're not involved at all. Right, so that as this wire is rotating around, it is always in contact with this ring. And while this wire is going around, I had those going in opposite directions, that's obviously not the case, it's always in contact with that ring. And then we have these going out such that we can have current flowing through them. And so there's some kind of metal brush on the wire or what have you that will be in contact with this slip ring the whole time. And so we have a loop of wire. It's rotating. It's in an external magnetic field. So we expect to induce some EMF, which is going to induce a current or create a current. And we can look at that from both sides. And so this is the setup we have. If we wanted to take this and figure out what the EMF is going to do, well, we can have the EMF as a function of time is equal to some amplitude times sine omega dt. Right, I think we've seen in class briefly that if we have phi sub b is equal to the integral b dot dA, we can rewrite this as BA cosine theta, where theta is the angle between the area vector and the magnetic field. And so then we can write it as BA cosine omega t because we have theta is equal to omega t, right? Just like you could have x is equal to vt You know, same idea. And so then if we take EMF is equal to negative d phi dt, this looks like a partial, that's not true, d phi dt, you get that the EMF is going to follow a sign, right? And so that's more or less where this comes from. And so, let's think here. This omega d, we can call this the driving frequency. And that's going to be the frequency at which this is rotating. Okay? Yeah. And so this M, so this is going to be the max EMF, which is going to be true when the sinusoid is equal to 1. And so here we have equation 3128. And if we wanted to find the current as a function of time, we could say the current is equal to some max value times sine omega dt, and then we can add a phase in there. Because as we will see, these are not always in phase, right? If there happens to be some kind of an inductor somewhere, it's going to initially resist the EMF, and we're going to have all sorts of fun things happen. But we're not jumping into there quite yet. So that's all you need to know from this section about AC, and then we'll hop into 31.7, which is forced oscillations, often called driven oscillations. And so for that, we're going to start with a circuit that has some alternating current with an EMF. We're initially going to say the EMF is pointing in this direction. We have a resistor, we have a capacitor, we have an inductor. And they're all going to have current traveling through this loop. And so let's start by making the assumption so assume the resistance is small. In that way, we can kind of look at this expression here, and what's going to happen if we have a very, very small resistance. We end up with omega prime is approximately equal to omega 1 over LC. Right, and we're doing the same game we've done through, the entire year, last semester, this semester. When we're introducing a new thing, like a driving alternating current, we're going to try to simplify it as much as possible to figure out how the basics work, and then we'll build from there. And so let's see. Well, let's kind of compare, and we can say this is going to be the natural frequency or the resonance frequency. And I guess if we wanted to be more correct, which of course we do, the natural angular frequency. Okay. And so I guess let's briefly harken back to our block on a spring. And so if we have some natural frequency, square root k over m, what can we say about this? If we were to pull this out and let it go, that's the frequency it would oscillate with. But now imagine that you're going to take this and you're just going to apply some external force. Actually, we could probably also just make it an impulse. Where that's momentum over time. But a force is just fine, as long as we keep in mind it's not going to be a constant force. We're just going to maybe every so often take this and smack it, right? That's going to change the way this oscillates, right? If you were to apply this force at this frequency, then you get resonance, and you're going to kind of, like kicking your legs on a swing, right? You kick your legs every time you're at the peak of oscillation, and that's what makes you oscillate more and more. Very similar like this, if every time this block gets to its amplitude, we smack it, we add more energy going back, then it's just going to get a bigger and bigger and bigger amplitude as we go. Right, and so that's if you drive it at its natural frequency, you get resonance, and you get like a feedback loop. Like you keep getting more and more oscillation out of it. But you could also think, what happens if you hit it at some other time, right? And I don't know if you've ever just been bad at being on a swing. If you try pumping your legs, in like the wrong direction, or while you're, in the middle or something like that, it feels weird, right? You're not smoothly oscillating anymore, and you can feel that. And so, very similarly, if we were to smack it at some other frequency, we can start to kind of force the oscillations to occur at some other frequency. And so we can say whatever the natural angular frequency, omega, of a circuit may be, forced oscillations of charge, current, and potential difference in the circuit always occur at the driving frequency. And which, this should kind of make sense, right? If it doesn't really matter what the capacitor or the inductor want to do, if we take this power supply and we decide we are flipping the current, Lenz's law is still going to come into play. It's going to resist for a bit, but the moment we flip the outside current, even if we're not fully charged on this capacitor, the moment we flip it, the charges are going to start leaving. It's not going to care that, oh no, I still have some positive charges coming this way. The moment we flip it, those positive charges are going to be like, well, I'm traveling this way now, I guess. And same for everything else in the circuit. And so you can force it to oscillate at its non-natural frequency. But then we keep in mind, so we will see that the amplitudes of oscillations of the depend on how close omega d is to omega. So the driving frequency is to the natural frequency, right? And if you can imagine, let's say we are alternating our potential, our EMF, right, or the applied voltage, incredibly fast, right? Like faster than anyone has any business doing anything. And I say maybe we start with no charge in the circuit, and so maybe we only get one positive charge, one negative charge, and then we flip it. Well, the Q, the amplitude of oscillation, is going to be small because we're going too fast for a significant amount of charge to build up, right? And then, and so that's the idea, is that if we are driving it at a non-natural frequency, it can't reach its full amplitudes for things, and so you can diminish the overall amplitude. When the two match, the amplitude is maximized. And so we can wrap it up there for today. Alrighty.